In this video, we're going to look at two application examples of differential equations and how they pertain to exponential growth and exponential decay. And for these two examples, you're going to want to have a calculator with you. So make sure you have that with you as you watch this video and maybe try these examples together with me. So here's the first one. This one is talking about population growth. It says that the population of the town of Scorpion Gulch is now 1,000 people, and that population is growing at the rate of 5% per year. So where you see that phrase per year, there's the rate. And calculus is the study of rates, and so we have a derivative concept right there with this population growth rate. And part A says to write a differential equation that expresses this fact. Now, what's happening here in this situation is that the rate of population growth, the rate at which the population is increasing or is changing, varies directly with the present population. And if you recall, direct variation involves this constant of proportionality. I'll call it K. So I'll write this diffie dp dt, where capital P is population and T is time. Time will be time in years. So dp dt is equal to K, that constant of proportionality, times P, the population growth. Now, we know that the population is growing at the rate of 5% per year, so that would be the constant of proportionality in this problem. So I'm going to write down on this problem here that dp dt is equal to 0.05 times P. So that would be our differential equation that expresses the fact that the population is growing by 5% per year. Now, part B says to solve that differential equation to find what will be essentially the particular equation that will express the population as a function of time. So basically, the part B is asking me for the particular solution of that diffie. Find capital P of t, P as a function of t time. So here we go, dp dt equals 0.05 times capital P. So first step is to separate the variables. So let's call that, if I divide by P, 1 over P, dp equals 0.05 times dt. Separate, next step comes the integration step. So natural log of the absolute value of P is equal to 0.05 t plus c. And if we exponentiate both sides involving e, so then I'm going to have P in absolute value bars equals e to the power of 0.05 t plus c, which is simply c times e to the 0.05 t. All right, there we have it. And then if we solve for c, notice that the initial condition up above was that presently the population is 1,000 people. So we'll use 0, 1,000 as that initial condition. And let's plug in 1,000 for P, c e to the power of 0.05 times t. Or actually t would be 0 here. And e to the power of 0 is 1, so I find that my c value is going to be positive 1,000. And so with that, I can write down what is the particular solution. So P of t, population as a function of time, would be 1,000 times e to the power of 0.05 t. And that would be sort of the particular solution to this differential equation. Back here in pink, I essentially have the general solution right there. And now with this population equation or this model, I can approximate the population of this town at any given time. I can plug in any sort of input for t, and then I could generate the output for p, population. So that's how I can go from the differential equation all the way to that particular solution and then use it to answer questions or interpolate data questions regarding the situation. Okay, so one more example, number 2. This one involves light intensity. So the light intensity as you sort of dive beneath the surface of the ocean satisfies this differential equation right here. dl dx equals negative k times l. So now there's a negative sign on the constant of proportionality. And we kind of know just sort of from experience that the deeper you go, the farther away from the surface of the ocean, of the water, the less light there is. So the light intensity sort of decreases the deeper you go. And so the question here says that you cannot work without artificial light when the intensity falls below 1/10 of the surface level value. About how deep can you expect to work without artificial light? So here's this diffie-q, dl dx, where L represents light intensity and x is the distance in feet beneath the surface of the water. Now, let me just make a table of comparison here. So let's call this x for feet, and then L of x would be light intensity. So essentially we have at 0, which would be the water's surface, you have some light intensity. We'll call that C. And then notice this statement here, diving to 18 feet in the Caribbean Sea cuts the intensity in half. So when you're 18 feet down, then we have half light intensity. So I'll use 1/2 of C. And then it says, how deep can you go without using artificial light, which would be anything below 1/10 of the surface value there. So the question mark is, how deep can we go here when that light intensity is 1/10 of the surface level value? So there's kind of a little input-output table just to sort of help me frame the question and to focus my thinking somewhat. Back to the differential equation now. If you solve any kind of differential equation that has this constant of proportionality times this dependent variable, you can jump right to that general solution. It's simply going to be L equals C e to the negative k times x. And if you don't believe me, go back and check out example number 1 and look at the process that we did by separating, integrating, and then isolating that variable. We're going to always end up with this form for the general solution. So I'm going to just jump right there to that step and try to now use the given conditions to solve for the particular solution here. Well, I would just use this 18, 1/2 C as a condition to just sort of check and evaluate. So let's plug in 1/2 C for L. And I have C e to the negative k times 18, x equals 18. So I don't know what that constant of proportionality is here in this differential equation. I have to solve it. Well, in this case, the c's cancel out. So 1/2 is equal to e to the negative 18 times k. And if I take the log of both sides, I can get the log of 1/2 equals negative 18k. And so my k value will end up being the natural log of 1/2 divided by negative 18. So I would take your calculator right now and compute that. And don't round too soon. We never want to round prematurely in calculus. But in advance, I checked this out. If you could confirm that for me, I got 0.038508 and some other decimals after that. But there would be my approximate value for k. K is the constant of proportionality. Now, we haven't solved for C yet. That's simply k. All right, so don't confuse the constants. We might generate a number of constants in these differential equation applications. But now we're going back to this table here, and the question said, what is this? How deep can we dive without worrying about that artificial light? So let's plug in now 1/10 C into our equation. L, light intensity, equals C e to the power of k, but k is now equal to this, negative 0.038508 times x. There's my k value. Let's plug in 1/10 of C for light intensity. And now I can solve for x. The constants again will divide out. I can divide both sides by C. And I have one equation now with one unknown, so I'm ready to solve. All right, let's see here. Looking for x, so I want to take the log of both sides. Once again, the log of 1/10 equals negative 0.038508 times x. And then finally, divide both sides by the decimal right there, and we'll have x isolated. So check with your calculator. X should be approximately equal to 59.5. let's see here, I got 59.795 feet. All right, so that's about how deep we can go, at which point we'll have the 1/10 light intensity of the surface, and so we'll need artificial light before we dive any deeper than about 59.795 feet. So those are two examples of how we can sort of use differential equations in these exponential growth and exponential decay applications. I hope that was helpful to you, and I'll look for another couple videos in the next couple days with a couple more examples where we cover some different styles of questions and how we can see these differential equations involved in a variety of other applications as well. But for now, feel free to email me with any questions, and I hope those two examples were helpful for today.